Good morning, everyone. So thanks a lot for attending the meeting. This is Ming-Xu from Oak Ridge National Lab. I'm a domain scientist and interested in accelerating the weather and climate models using GPUs. So here I'm going to present our efforts on optimizing radiation and cloud aerosol microphysics submodels from the UK Meta Office, the state-of-the-art unified model. The project is a collaboration among the Oak Ridge National Lab and the Meta Office and the US Air Force. So first, I would like to thank my colleagues from Oak Ridge National Lab. They are Mario, Matt, and Salim, and Valentin, and Kate, and James, and Chris from UK Meta Office. The outline of my talk is listed below. So first, I will give a brief introduction and the motivation of this work. Secondly, I will introduce the models and the machines we are working on. And third, I will going to discuss the methodology followed by the experiments and the benchmark. Fourth, I will show some results. Then I'm like to share some lessons I learned during this work. And at last, the future plan and the conclusion will be discussed. So atmospheric radiative transport model and the cloud aerosol microphysics schemes are usually the two most computational intensive parts of weather and climate models. Modeling them accurately is important for energy balance and overall model performance. But more accurate schemes generally need more computational resource and are not feasible for global forecasts and simulations. So leveraged by those heterogeneous computing systems, especially by the potential of the GPU computing. So we have been trying to port the computational intensive parts of an RTM and a microphysics model on GPU to speed up their calculations. So the RTM and the microphysics models that we are working on are Sockit and CASIN from the Meta Office Unified Model respectively. So Sockit is the abbreviation of the suite of the community radiative transfer codes based on Edwards and Slinger. So it is the default radiative transfer model of Meta Office Unified Model. It has various physical options, including multiple solvers and schemes. And it is a 14 code and with several C codes. And the total number of the source code line is close to the 124K and includes some comments. So it is a serial model. So the parallelism is expressed in the unified model, its host model or the offline models. So the difficulties for accelerate porting is there are multiple levels of nested subroutine calling structures, and it is highly optimized for CPU computing. So it may be not feasible for GPU computing. And loops either in the topmost subroutines or in the deepest subroutines. So, and it is hard to keep a memory coalescing when arrays are promoted or demoted. Oh, sorry. CASIN is a cloud aerosol interacting microphysics. So it's a long-term replacement of the unified cloud microphysics. So detailed representation of aerosol effect and in cloud processing. So we can get more realistic simulations. It's 1419 code and has 116 subroutines and the total is close to the 16K lines. So it is a good candidate for running parallelly on GPU because the vertical columns are independent. But the difficulty for accelerated porting is there's a lot of overhead due to a lot of function calls. And the thread divergence due to if statement and some data dependence over the vertical loops. So the machine we are working on is from the Oak Ridge Leadership Computing Facility Summit machine. So each node, it includes 2 IBM Power 9 CPUs and 6 NVIDIA V100 GPUs. So the latest build environment on Summit for our GPU acceleration work is we basically use the PGI 1949 compiler. And we also use the clock compiler. This is source-to-source compiler, so we can implement the OpenACC automatically. And then we use the GPTO. This is a general purpose timing library for the performance profiling. So as a prototype, so we first focused on the random overlapping and gaseous absorbing scheme. This is one of the most expensive and accurate scheme in Sockit. So we first port the model to the OSCF machines, then we will profile the code to identify the computational intensive paths, those hotspots. And then we'll implement OpenACC directives into the code manually or automatically by using the clock compiler. Then we'll measure the computational performance and then verify and validate the results. So we'll continuously repeat the steps from 2 to 5 till we achieve our goals. So this slide shows the code structure and the profiling. The left figure illustrates the calling structure and the performance profiling results of a test run of Sockit. So the y-axis is the subroutine names, and the top x-axis is the word time, and the bottom x-axis is the number of calls. The order of calling subroutine is from top to bottom, and the space indentations before subroutine names indicate that subroutines are called at the above subroutine. So we can see the radiance calc calls the sole band random overlap, and the sole band random overlap will call the gas optical properties and monochromatic ratings and argument ratings. And the radiance calc is the major interface for Sockit to interact with the offline test codes and the UM model. So we can see the Sockit has the multiple levels of nested subroutines. So it is very common for the codes that are highly optimized for CPU computing and memory usage. The location, we also show the locations of the major loops, such as those wave bands, the ESFT loop, also known as K loop, and the vertical loop I, and the horizontal loop L are also shown on the figure 2. So the band loop covers all subroutines as we see in the figure. And inside it is the K loop, then the L and I loops, and exist in the very deep subroutines. So from figure, we can see nearly all of its time is consumed by its subroutine called the sole band random overlap. And in the sole band random overlap, most time is used by the monochromatic radiance. And in the monochromatic radiance, the monochromatic radiance and score TSEQ consume most of time. And then in this monochromatic radiance TSEQ, the mixed column use the most of time. So this is nested subroutine calling structure. And so about more than 8% of total time is consumed in the mixed calling subroutine. So we are going to look into this subroutine. We identify 3 hotspots, and I make the red circle on the figure. So there are trans source coefficients and the 2 coefficients cloud and the sole mixed director, which are consumed 27 and 12 and 36% of total time respectively. So there are many ways to optimize the code for GPU accelerations based on those kind of loop structure. I first try to push the horizontal loop up, and combine it with the K loop and make the sole band random overlap to be a single column model. That means we without any horizontal dependence and this subroutine. And all subroutines and the sole band random overlap will be included into a bigger kernel. The GPU gain and work parallelism is applied to the K and the horizontal loop. And the vertical loops in the bigger kernel are implemented by using the vector parallelism. Hereafter, we call this method is a push-up method. So as a domain scientist, I like the method as it is very clean and simple by putting all the calculations into a kernel. Moreover, we can use the single column abstraction of the clock compiler to implement OpenACC directives automatically. And instead of about this kind of one big kernel, we also can push down the K loop to the deep subroutines that we identify as hotspots and combine them to set up several small kernels. So hereafter we call it the push down method. So we have two methods to try. And this slide shows the loop structure as we have seen in the previous slide. So I just want to emphasize how deep these hotspots that in this calling structure. And also the loops are separated widely by those nested subroutines. This gives us a lot of hard time to reflect the code. So I omit those kind of code reflecting how we did it, but I just want to mention that we try our best to make sure that the modified version with the GPU accelerations has a similar performance as the original CPU versions when it is run on the CPU. And this slide shows the default compiler options. So we use the PGI compiler, and just for the GPU, we use the unified memory to simplify the data movement right now. And this slide shows how we implement the single column abstraction. So it's very simple. We just put one crawl directives before the horizontal loop. And then in the single column model called the solve band random overlap, we add two crawl directives. One just used to define the horizontal dimension name, and the other indicates that we want to use the crawl single column abstraction features. So after the code is compiled by the clock compiler, so we can see the OpenACC directives are inserted to the single column model automatically. And we also can see the horizontal loop is pushed back to this single column model. And correspondingly, the horizontal dimension is also added back to the arrays in this single column model and all the subroutine in it. So it's very simple to use the clock compiler. So, and then we want to do the two experiments were conducted with different methodological forcing. But from the performance view, so the earning different is their dimensions are different. So one is a small size of the horizontal dimension. It has earning 20 grids. And the other is have a large horizontal dimension size is 1,500 grids. So the benchmarks, we are trying to compare the performance of the CPU earning theory and the GPU acceleration runs. And we also estimate the node performance of the CPU earning and the GPU acceleration parallel runs. So let's go to the results. So the slides show the result of the push-up method. So the left figure shows the kernel running time as a function of the number of GANs, works, and vectors. The blue line is the running time of the series CPU earning run. So we can see the performance of the GPU acceleration run is worse than that of the series CPU run in some case. So the most speed up we can get is 1.32 times speed up when we use 80 GANs and 2 workers and 32 vectors. So the poor performance of the push-up method is mainly due to first is many levels of nested subroutines in the bigger kernel consume the GPU registers and memory quickly. And second is any GAN and work parallelisms can be used to horizontal and K loop. And the number of GANs and work is limited. So if we try to give the large number of GANs and works will cause out of memory errors. So how about the pushdown method? So we show the results of the pushdown method. The left and the right figures are results with different horizontal dimension size. One is 20 grids and the other is 1,500 grids. And the y-axis is speed up value and the x-axis is the number of the K loop. So from the figure, we can see that the GPU acceleration runs generally have the 3 and 8 times speed up for the small and large size of the horizontal dimensions compared with the CPU earning serial runs. And the next slide, we show the performance of individual kernels. So the x-axis is still the subroutine name in which kernel are implemented. And the y-axis is the speed up value. So we can see the hotspots that we identified in the previous slides get 8 to 15 times fast in the GPU acceleration run than the CPU earning runs. So the performance gains in the pushdown method are due mainly to we have the small kernels on the hotspot, and the GPU parallelism such as gun work and the vector is fully used in the hotspot. So we also evaluate the node performance of the pushdown method. So we will compare the following two runs with a total 9,000 grids on a summit node to compute the speed up approximately. So first is GPU acceleration run. We will run Sockits in 6 GPUs simultaneously with 1,500 grids per GPU. And the CPU earning run, we will run the Sockits in 42 CPU cores simultaneously and with earning 214 grids per CPU cores. So these two runs, we have the same size of the horizontal dimension. And also these experiments account for the memory and the cache computation in a node. So the left figure shows the results, and we can see the y-axis is still the GPU acceleration and the speed up values, and the x-axis is the number of the K loop. So we can see the GPU acceleration run can gain maybe from 1.75 to 1.95 speed up compared with the CPU only run on the on node level. So let's look at the CASIN results. So the CASIN, we're using the 2D scoreline case driven by the kinematic drive model, KID model. So currently we use OpenACC to achieve a two-level parallelism. GAN is for the out horizontal loop and the vector for the inner loops. So the right figure shows the speed up. So we can see generally the GPU, the speed up for the CASIN in the GPU acceleration run is 2 and 3.5 times speed up compared with the serial run on the summit. So the load blocks and the lessons learned during this kind of porting work. So we found that there's a lot of heavy code refactoring efforts. So it cost us 2 and 3 months and 1.5 months to implement the push-up method with the single column abstraction and the push-down method, respectively. And it is difficult to merge the above developments to the main trunk and the other branches of Sockits and CASIN, as their code base are substantially different. So we are working closely with the Meta Office colleagues to try to how to merge our development to their repositories. And some 1419 features are infeasible for GPU portings. So for example, the derived data type. So kind of we just expand their memo variables and put them into the subroutine. And calling multiple levels of nested subroutines caused large overheads and used up available GPU register and the memories. So big kernel maybe is not a very good choice. And the loops are separated in different levels of nested subroutines. So it is hard to combine them to use GPU efficiently. And the memory coalescing is hard to maintain when arrays are promoted and demoted in this kind of situation. So have multiple levels of nested subroutine structure. And the conclusion, so we were applying the single column abstraction of the clock compiler on some top level subroutines. Could be useful for GPU porting in the Pushup method. However, the multiple levels of nested subroutine in the big kernel easily cause an out-of-memory error and prevent the vector parallelism from expressing on the uppermost loops. And besides, the big kernel will let GPU do other tasks than the loops that are usually not optimal for GPU. So consequently, we only got 1.62 times speed up. And pushing the K loop down to the deepest subroutines can reach approximately 3 and 8 times speed up when the number of the horizontal grids is small and large, respectively. We also estimated the node performance of the CPU earning and the GPU acceleration runs on Summit, and found that there are nearly 2 times speed up per node for the GPU acceleration runs using the pushdown method. The speed up for CASIN in KID are 2 and 3.5 times depending on the number of the columns. So our future plans, we want to still using the single column abstraction using clock compiler because it is easy and can do this kind of automatically implementation of the OpenACC directives, and also can give you some performance portabilities so it can compile to the OpenMP directives too. So we want to apply the single column abstraction in a deep subroutine, for example, the missed column subroutine to elevate the pressure from GPU in the Pushup method, and improve the data locality by changing the unified memory to explicit OpenACC data directives, and increase the concurrency of launch kernels. Currently, we don't have any concurrency in the GPU code, and the overlaps of the kernel and the memory copies. So for example, the kernels in the clear sky and the cloud sky radiation calculation can be launched synchronously. And the short wave and the long wave radiation can be computed in a different GPU simultaneously in the future. And we also enhanced the memory copy throughput. So currently the average throughput is very low, only 450 megabytes per second. So we have plenty of rooms to improve it. And we will run the offline and online Sockits and CASIN on a Summit node to improve their node performance, and then verify and validate the results from the GPU offloading codes. So the difference in the results of the GPU acceleration and the CPU earning runs are very small. So about 10 to the power negative 7. They are definitely not bit for bit. So from the climate aspect, we only care if the run generates the same climate. So we will apply our colleagues' work, Salim Mahaji's work, to verify the climate reproducibility on the GPU acceleration results when we continuously optimize the model performance. So this method has been implemented in the regular test suite of the DOE E3SM system model development. And I would like to thank our funding support. So this research was supported by the US Air Force LCMC collaboration with Oxygen National Lab, and the computer resource is provided by the Director's Discretion Project. I'll stop here and take questions. Thanks. Okay, there are 2 questions. May I miss this? How was the CPU performance made for the speed up calculations? So the CPU performance is measured using the GPTL time library, and they have the 2 comparisons in my talk. One is we will compare the one GPU performance versus one CPU core performance. We also call it the CPU ending serial run. And we also compare the performance on a sample node. So we will compare the performance of the 6 GPU simulations and compare with the 42 CPU cores runs. And the second question, have you observed any kernel core performance difference between use the manager flag and not use the manager memory flag? Yes, this is a good question. Currently, I focused on the loop structures first. So I did not try using the explicit OpenACC data directives to control the data movement. So I only use the manager this is kind of unifying the memory options in OpenAC in the PGI compiler. And the third question, perhaps you mentioned, just for clarification, did you use all GPUs in the node? If not, how many were used? Oh, yeah, maybe I'm not did not make it clear. So, so in the first results, I compare the performance using the one GPU and versus one CPU cores. And on those kind of node level performance, I use all the 6 GPU in a summit node and all the CPU cores in a summit node.